Hi, my name is Philipp Meyer from Hamburg University of Applied Sciences, and I would like to introduce our work on anomaly detection in real-time networks using asynchronous traffic shaping. This work was done together with Teresa Lübeck, Timo Salomon, Franz Korff and Thomas Schmidt. We start with a short overview. First, I would like to introduce what motivated us to detect anomalies in real-time networks. Afterwards, I explain how we use asynchronous traffic shaping for detection of anomalies. Then I will show you aspects of our benchmarks and finish with conclusion and outlook. Reliability and predictability are essential in safety-critical applications such as in vehicular communication. Traditional Ethernet protocols often struggle to meet these demands, leading to jitter and unpredictable latency. Time-sensitive networking adds technologies and shaping mechanisms such as asynchronous traffic shaping. Developers can create robust networks while maintaining sub-millisecond latency. In-car networks are vulnerable to misbehaving communication with the potential for catastrophic outcomes. Even a single anomaly can have severe consequences when milliseconds are crucial. For example, an unexpected latency spike could delay brake signals. Those anomalies can be caused by misconfigurations, defects, and cyber attacks. Anomaly detection identifies misbehavior and enables countermeasures to address them promptly, minimizing the risk of extended damage. Therefore, network anomaly detection is a vital component for ensuring the reliable and predictable transmission of safety-critical data in vehicles. Despite its importance, network anomaly detection is prone to false positives. In onboard networks with fast communication cycles, even a precision of 99.9991% can result in one false positive every 8 operating hours. These false positives may trigger unnecessary countermeasures such as blocking legitimate traffic or notifying operators of non-existent issues. This disruption of frequency is unacceptable for drivers that would not accept false alarms or even losing functionality every few hours. Therefore, anomaly detection systems in real-time networks that automatically trigger responses must maintain extremely high precision to avoid degrading reliability rather than enhancing it. In previous work, we proposed anomaly detection that uses TSN per-stream filtering and policing as a descriptor of valid traffic behavior. When configured correctly, our approach can detect fundamental misbehavior in real-time networks without false positives. But has asynchronous traffic shaping the potential to improve detections? RTS is an addition to TSN, where the shaping is calculated at ingress. When deploying ATS, configuration is already essential for communication of critical driving functions. Independently from PSFP, this configuration can also be used for anomaly detection. So how can we exploit asynchronous traffic shaping for anomaly detection? ATS is a token bucket-based per-stream shaping algorithm that operates without time synchronization. The committed information rate defines the flow of tokens into the bucket. The committed burst size defines the size of the bucket. Typically, one scheduler per port and stream determines the point in time when frames become eligible for transmission. After ingress scheduling, frames are forwarded to the egress queues, where they are sorted by eligibility time. Transmission is only allowed by the time of the earliest frame's eligibility timestamp. The maximum residence time limits the maximum eligibility time delta. The figure illustrates the ATS scheduler algorithm. Frames 1 to 5 arrive as a burst. The CBS permits a burst of 2 frames, allowing frames 1 and 2 to be assigned eligibility times matching their arrival time. When frame 3 arrives, available tokens have been consumed by the previous frames, and the eligibility time is set to the earliest time when enough tokens are available again. The same would apply for frame 4, but since its eligibility time delta exceeds the MRT, the scheduler discards it. For frame 5, the eligibility time delta is again shorter than the MRT. 2 further aspects are relevant. Firstly, schedulers are organized in groups. There's one group per incoming port and upstream traffic class. Each group keeps order in priority classes already shaped in the previous hop. The group eligibility time always holds the most recent eligibility time assigned by any scheduler of the group. Every new eligibility time must be greater or equal to the most recent eligibility time of the group. Secondly, ATS frame size is limited by the CVS. Prior data unit size filtering is mandatory. With a valid ATS configuration that is strict and also not result in frame discards in valid traffic scenarios, we can use discarded frames as an indicator of abnormal behavior. The figure shows the architecture of our distributed network anomaly detection system, which comprises any number of TSN switches and one central instance. The central network controller or manager contains an application that observes relevant counters using protocols such as SNMP, NetConf, or OpenFlow. When a change in chosen statistics is detected, it indicates an anomaly. Upon detection, a controller would also be able to deploy countermeasures such as blocking specific traffic or reporting the anomaly to a higher level. For example, in the figure, scheduler 0 in port 0 of switch 0 discards a frame because of an ATS scheduler violation. Therefore, the discarded frames count is incremented. This change is then detected in the NADS application. We can now put the design under test. In the following benchmark, the detection uses only the observations of statistics for frame discards because of frame size and maximum residence time violations. The benchmark is run on a simulation environment based on OmNet++. We use a minimal network topology consisting of one switch and two end systems. Since each TSN ingress operates independently to the broader context, the benchmark topology effectively represents an arbitrary hop in any network. All scenarios share two basic traffic configurations. All traffic flows from the source to the sink host. All links have a speed of 100 Mbit per second. All devices are configured with respective egress shaping for TSN traffic. Anomalies are infused on application or link layer in the source host, and we observe the statistics of the switch. Our benchmark reflects a heterogeneous environment with practical relevance using different types of concurrent traffic. All network devices experience local clock drift and are synchronized using GPTP. The asynchronous data stream is shaped by ATS. A second configuration increases the number of ATS streams from 1 to 2, integrating a case where the group eligibility time is a decisive factor. Therefore, the single data stream is split into two concurrent streams with the same priority and total bandwidth by doubling the length of the production interval. We use the baseline traffic scenarios without misbehavior to find configurations with 0 drops from 20 CBS and MRT combinations. The figures show a heat map of the number of drop frames in dependence to CBS and MRT for both basic configurations. Regarding frame drops, one parameter can render the other insignificant. One can argue to always set the MRT to 0 and compensate this with a higher CBS value. In this case, there must be enough tokens that the maximum burst can be processed without delay. Alternatively, one can set the CBS to the minimum frame size and use the MRT to compensate. This way, the burst size on each hop do not need to be considered, and ATS stretches all incoming bursts on each hop. So, MRT and CBS can be weighted against each other. To obtain distinct findings, we proceed with the edge cases marked with a green circle. A total of 3 million frames are traversing the ATS scheduler in these 4 settings with 0 drops. So, there are no false positives in any of the valid scenarios. We infuse 5 fundamental anomaly classes with a minimum clearance of 1 millisecond and a probability of 50%. Elimination, existing frames are dropped. Injection, new frames are injected with uniformly distributed size. Manipulation, payload content of the frames is changed. The new payload size is also uniformly distributed. Reordering, the order of frames is changed. One frame is taken and reinserted after the next frame of the stream. Rescheduling, frames are delayed by random delta up to 125 microseconds. Other frames can pass while the frame is delayed. All complex traffic misbehavior like attacks fall into at least one or combinations of these link layer anomalies. This table presents the number of true positive and false negative detections along with the resulting recall for each anomaly class in the single stream scenarios. The absence of false positives always lead to a perfect precision. In application layer scenarios, the anomalies are infused before TSN shaping. In link layer scenarios, the anomalies are infused after TSN shaping. For comparison, we show further scenarios where ATS is replaced with credit-based shaping and PSFP metering is used for anomaly detection. we compare with 3 different PSFP metering configurations. The first shows the data stream detection results from previous work using a custom credit-based metering algorithm. The second is using statistics of a standard token bucket meter. The third is the same as the previous configuration, but with the addition of also using data size filtering statistics of the stream filters to increase comparability with ATS, where this is mandatory. In general, elimination is not detectable with either of the shown approaches. A small number of detections occur in the ATS configurations. In those edge cases, even slight misbehavior is enough to trigger discards. The credit-based streams detection performance varies based on where anomalies are introduced. The CBM is a precise credit-based shaper counterpart, and thus the credit-based shaper hides all misbehavior from the CBM. Link layer intrusions are detected with high recall because they violate the credit-based shaping behavior. Token-based ingress metering can detect application and link layer injections. The recall increases when the size filter is added because all injected frames that are larger than the original frames are dropped. ATS can further improve the detection of injections. For both injection layers, the ATS configuration with an MRT of 300 has the highest recall. Manipulation changes the stream's data rate, but unlike injection, doesn't always increase it. The data rate may also decrease in phases with smaller frames. In all credit-based cases, recall is lower than with injections, as reduced data rates do not violate these metering algorithms. Among all tested methods, ATS shows the highest detection rates for manipulation. Once again, the ATS configuration with an MRT of 300 performs the best. Reordering and rescheduling can sometimes create larger bursts when a removed frame is reinserted, even if the overall data rate stays the same. In the 3 credit-based stream configurations, only marginal detections are possible. Overall, none of these 3 methods can reliably detect them regardless of the layer. With the ATS scheduler, detection of reordering and scheduling is possible with low recall. The major difference in performance between ATS and token-based metering demonstrates that the ATS enables tighter mapping of stream behavior. In summary, ATS enables higher detection rates while maintaining 0 false positives. Further, detection of reordering and rescheduling is possible, which is not possible with the tested alternatives. The results with 2 concurrent ATS streams show the same trend with one major difference. Here the concurrent ATS streams share the same group. When an ATS scheduler of another stream sets an eligibility time, the subsequent eligibility time for the current stream must not be earlier than this. Consequently, another ATS scheduler might cause the MRT value to be exceeded. The ATS setup with an MRT of 200 detects reordering with perfect recall, regardless of the anomaly infusion layer. This is because ATS is sensitive to the frame order of different streams within a single group. Setting the MRT value to 0 prevents the ATS scheduler from calculating future eligibility times. Instead, it can only check if arriving frames are eligible based on the arrival time token count. This suggests that an adjusted MRT value increases the ATS scheduler's sensitivity to the frame order, which in our case also enhances detection performance. In conclusion, we use the ATS configuration to effectively describe normal system behavior without requiring separate configurations or resources. Our evaluation of the ATS parameter space reveals that the CBS and MRT must be weighted against each other to find valid configurations. ATS improves detection rates in comparison to PSFP-based approaches while maintaining 0 false positives. Our benchmarks show that all our fundamental anomaly classes, except elimination, can be detected to different degrees without using our approach. Thus, at the current stage, the proposed NADS satisfies key requirements for in-vehicular deployment. Multiple future research items arise from our work. Testing our approach in real-world scenarios or with industry-standard TSN hardware could provide even deeper insights into its applicability and feasibility. Using real attack traces could further expand detection insights. Finally, comparing against dedicated detection algorithms could quantify the trade-off between false positive and detection capabilities. Thank you for your attention. All our simulations are available open source.